almost 7:50, so yeah, I can start with some general announcements. So other than these lectures, we don't have anything scheduled for the next month or so. We are waiting to hear back from the parks whether they will open soon, but as soon as we get notification that they're open, we will check with them on permits and everything else so that we can reschedule our members only nights at the very least to begin with. I don't think there will be public nights for the rest of the year, even if the parks reopen. But we have been discussing at the board having the members' nights open again. We just need to wait for the parks to give us notice.
They have those last-minute fire alerts where they close it down at the last minute too.
Yeah.
And where there's little fires popping up in Marin.
So as soon as we have a date for a members' start party, we will actually announce it on the weekly email that goes out and on the Facebook page so that anybody who's interested can attend. We will have some restrictions added on top of the ones we already had because of social distancing, and so we will announce those as well. We've been discussing a few other things to do virtually. We were thinking of having a start party virtually where people can connect their telescopes to Zoom and share what their telescope is seeing. Hopefully we can pull that off with some of our members and maybe attract some of the general public who might be interested in astronomy. But that's as a way to relieve our, I guess, lack of start parties from being locked down. We are thinking of doing that. It's also educational, so it will have maybe a different audience than typically we have for a start party.
Do you know if the Randall has any events on their premises these days or not?
I know for sure they're not.
They're not, still, okay. I didn't think close, so, yeah. But yeah.
Yeah, with the schools still closed and the Randall being part of the school system.
Oh, yeah.
They will not be open. It's not, I mean, even though it's public to the public, a lot of the content is geared towards the school district. So yeah, that's basically where we're at. For now, we'll have our lectures. We're thinking about virtual start parties soon, and hopefully at some point we'll get back to going to Montana. We will have guidelines on how to stay safe while sharing the night sky with each other.
Penny Boston was the last one speaking, and I was going to ask her to speak to us. She did a great job. I don't know if any of you saw her Mount Tam lecture. What was it, a week ago or so, but she was brilliant. And I would have asked for her to speak to us.
I'll check that on YouTube, actually. I bested. So Linda, do you want to do your announcement for the next speakers?
I can. Do you think it's okay if he might be starting sooner than 8 o'clock straight? What do you think?
Okay, true.
Hey, PJ, since you were just talking about virtual star parties with some of the people on this call that have those telescopes, I wonder if anyone on this Zoom session would be interested in participating. and letting everybody look through the eye of their unistellar. If we would start-
Jean-Pierre has one.
Having one and wanting to lead a virtual
He's here.
webinar are
He's-
two different things. So no
you could ask
pressure,
him.
but I wondered if anybody was interested. It sounds
Yeah.
intriguing.
So basically, the idea is to run Zoom on your phone, and the same phone you use to control your unistellar EV scope, and share your screen. Basically, will let us see what you're seeing on your scope. And then if we have multiple people connected, we can take turns showing what is in our telescope. So if 5 people show up, we have 5 things to look at, and switch from one to the other until we're all done, and then I'll look at something else.
I know that the Unistellar organization puts out sort of a calendar every week of things to observe in the night sky, as well as projects that are out there. And so some of those could be very interesting to the membership. Of course, not everyone has that telescope, so even knowing about the projects, I'm sure would be interesting. So we'd love to hear more from you guys, what you're seeing and what you're enjoying with those.
Okay. This is really interesting.
Anyway, I'll be in touch with those people that I know have TV scopes to organize a virtual start party and go over the operation side. Make sure that everybody's clear of what we're trying to do. If you have any ideas, feel free to email me at president@FAA. But we'll give it a try as soon as I have 4 or 5 people minimum to join us to make it an interesting start party.
What do you think? Should I wait a few minutes or not?
We have 5 minutes.
Yeah.
Hey, Linda, before you start, PJ, I wondered if you wanted to talk about iTelescope.
Oh yeah, there is a website called iTelescope that lets you rent out telescopes by the hour to take photos. And they also have a series of YouTube videos that are educational and that also show, it's kind of like a one-person start party where the speaker is using a night telescope scope and it's showing their current screen. And it's a talk about what they're looking at, whether it's M51, M13, whatever object they pick.
Are the telescopes in New Mexico?
New Mexico, Australia, Spain. There's at least one in California.
Right?
Yeah.
Okay. There's a great big star park that people have telescopes in New Mexico.
Yeah. But there's several companies that do this. iTelescope is only one of them. So the website is called itelescope.net. I use it for comet follow-up. When a new comet is discovered, they typically ask for people to provide observations to get the orbit, basically improve the orbit from the first observations. The more people observe and send data, the more accurate the orbit becomes. Orbit predictions, actually. I use those telescopes for that purpose. Okay, we have 3 minutes left. So you want to start, Linda? That should be for your.
Right. I'm Linda Mahan, and as many of you know, we always meet on the third Wednesday. August 19th, we have Simon Beerer from Kavli Institute for Particle Astrophysics and Cosmology at Stanford. His topic is probing fundamental physics with strong gravitational lensing. Many useful results for cosmology have come from this phenomena. Dr. Beerer will shed more light on how astronomers are utilizing strong gravitational lensing to probe the nature of dark matter and dark energy, the dominant yet unknown components of our universe. September the 16th, we have The Formation and Evolution of Binary Stars by Aaron T. Lee, who's professor of astronomy and physics at St. Mary's College of California. Nearly 50% of the stars we see are part of a binary system. Double stars and multiplicities of stars are a common phenomena in the Milky Way. Our speaker will discuss the process and how observations of stars and galaxies rely on our understanding of stellar binarity. And as so many of you know, there's nothing more wonderful to look at than a binary star or a triple star through the telescope, which is something that I love to see and love to do. With tonight's speaker, topic, let's see, Matthew Kroonblawd is a staff scientist in the Reaction Dynamics Group at Lawrence Livermore National Laboratory, where he first started as a postdoc under Near Goldman. He holds a BA in physics from the University of Minnesota, Morris, in 2012, and a PhD in chemistry from the University of Missouri, Columbia in 2016, where he studied with Tommy Sewell. His work is focused on developing computer simulation and modeling approaches to understanding how chemically reactive materials behave under dynamic and extreme conditions. He has over 20 publications on topics ranging from prebiotic chemistry to explosives and polymers. The topic, Did Comets Jumpstart Life on Earth? Is our speaker will discuss his research from recent observations confirming the presence of the protein-forming amino acid glycine in comets. This lends support to comet impact as a feasible pathway toward life on Earth. And we welcome Matt Kroonblawd.
Thank you very much for inviting me to speak to such a diverse group. Just a fair warning, you're in for a chemistry talk, although I do appreciate astronomy and science more generally. By training, I really am a physical chemist. So let me try and get this screen shared. And the talk up. Okay. So does that come through? It looks like it does on my video feed. So I guess first off, I really want to acknowledge the other folks who have worked on this, because even in a relatively small group, science is not an endeavor of a single person, but especially at places like Lawrence Livermore, we really work in groups as a mode of operation. In particular, I want to call out my postdoc mentor, Near Goldman, and colleagues Rebecca Lindsay, Brad Steele, and Will Kuo, who have all contributed at various points to this work, which is culminating in a larger question: did comets jumpstart life on Earth? What can we learn about the extreme chemistry of glycine through computer simulations? So to give some background for this, we actually have to go back to the mid-2000s when NASA sent out its Stardust probe. The point of this mission was to send a probe with an aerogel collector to go pass through the gas surrounding the comet Wild-2. Its aim was to collect samples of whatever might be there and send that in a capsule form back to Earth for analysis. Years later, when that capsule was arrived and chemists had a chance to look at it, what they found is really exciting. They found glycine, the simplest protein-forming amino acid, among the various constituents of that sample. Now, glycine is interesting because it's a fairly complex building block to start from in terms of setting off a cascade of prebiotic chemistry. Luckily, this wasn't just a one-off, and later when Europe sent their Rosetta space probe, they too found glycine in the periphery of a comet. For reference, Rosetta was the particular mission where they ended it spectacularly by throwing or plotting a trajectory for the probe to go into the comet itself. Now, both of these real-world observations lend credibility to some older theories from Carl Sagan, among other folks, that comets and meteorites might have actually delivered life-building molecules to an ancient Earth. And from that, set off a series of chemical reactions and sequence of building to larger molecules that now give rise to us today. Now we're really talking about fairly simple molecules. In this case, glycine has only 4 elements in it: hydrogen, carbon, nitrogen, and oxygen. But the organic chemistry that comes from glycine can be surprisingly rich, especially under extreme conditions. So what's so special about glycine besides it being an amino acid? Now, glycine and its chemistry have long been used as tools in a reductionist model to understand how polypeptides and other proteins form. The traditional chemical pathway for glycine chemistry is what's called a condensation reaction, or what's really a polymerization reaction. To start, we have simply 2 glycine molecules that, when they react, they form a carbon-nitrogen peptide bond that grows a chain, and we also produce a water, which is why we call this a condensation reaction, because we condense out water. If we repeat this procedure many times, due to whatever thermodynamic drivers we have, we can form much larger chains, or oligopeptides, ultimately culminating in the formation of much larger protein-like structures. Now, this standard route, using glycine alone as a backbone, doesn't really lead to profound chemistry, because the sorts of molecules one needs for life have far more complicated bases that have various functional groups on them. For instance, in this example here, you can see ring-like structures, other nitrogen-containing structures that are far more complicated than glycine itself. Glycine's really been looked at as a model for how you form the backbone, not necessarily the chemistry of the side groups. But we're interested in understanding the role glycine could have played in these extreme, astrologically relevant situations. To provide some context for what I view as extreme, and I know that by training I really am more of an explosives modeler than anything else, is that we're talking about extremely high temperatures and pressures, temperatures that are in the range of thousands of Kelvin. I put some imperial units for context. And more than the temperature, truly astronomical pressures from a human perspective. It's standard to work in high pressure chemistry and material science in the units of gigapascal, or GPa, where 1 GPa is 10,000 atmospheres, or the equivalent of having 60 miles of water over your head, far deeper than any ocean on Earth. But what these sorts of conditions do at a general level is the higher temperatures make atoms move faster, and the pressures push them closer together. And this can initiate some very strange chemistry compared to what you'd have, in the standard wet chemistry lab, at a university. But these conditions are really relevant to the sorts of situations that one would find this naturally occurring glycine under. A theory that has been long studied and I think is fairly well accepted is the notion that glycine and other molecules like this can form these long chains at submarine hydrothermal vents, black smokers like I show off to the right. Now, what's driving these reactions here is relatively modest swings in temperature that alter the various thermodynamic drivers. So you have glycine that starts out cold, and then it gets swept up into this hot pressurized plume where it facilitates the polymerization chemistry, and then it falls back out. And it can go through this cycle a number of times. And while a number of folks have looked at that, and if glycine ultimately makes it to the ocean, that's certainly a relevant pathway, we're interested in understanding how these more extreme conditions can really drive chemistry in situ. Now, in a cometary impact, the shock generated from that impact can drive materials through many different states, reaching thousands of degrees and tens of thousands, if not hundreds of thousands of atmospheres in pressure. And under those conditions, very unusual things can happen, and that will form roughly half of my talk. Another theory, which is much more recent, but is gaining some traction, is the notion that on various moons, or perhaps even on Earth itself, when you have tidal motions that cause shearing at various tectonic plates, that one generates both substantial pressures but also shearing forces. And those combined can drive various chemistry, but we really don't know much about it. So at the core of all of this is a simple question of trying to understand how a relatively simple molecule like glycine will react when we subject it to extreme conditions. The main workhorse tool when we're looking at these sorts of conditions is to go to computer modeling, because even if you, and in some cases you can perform actual lab experiments, but in order to better interpret those, we really need a modeling component to it to understand the underlying chemistry. Now, the workhorse tool that I rely upon is what's known as molecular dynamics, or more specifically, quantum-based molecular dynamics, or QMD. This is a relatively straightforward idea where we take Newton's equations of motion, just force equals mass times acceleration, here expressed as force is equal to the gradient of one's potential energy function, E. By obtaining the force, we can update the positions and velocities of atoms in our simulation cell. Once we've updated positions, we then evaluate the energy and go through this cycle. Now, what makes this quantum-based molecular dynamics is that we're obtaining that description of the forces, or more directly, the energies, by solving the Schrodinger equation. What I show over here is, from one point of view, the world's simplest chemistry problem, or the most complicated physics problem. What happens when you bring two lone hydrogen atoms together? Well, according to the Schrodinger equation, in isolation, a hydrogen atom will have a single electron associated with it, which we denote by this up arrow. And we have a second hydrogen atom with its electron far separated from it. Now, if we bring them together, the solutions to the Schrodinger equation tell us something about the electronic structure that results. Our initial electron clouds that surround our hydrogen atoms and are populated with a single electron now produce two new orbitals. So we have two atomic orbitals going to two molecular orbitals that describe the bonding and antibonding character of this interaction. For a particular orbital, we can fit two electrons in, and both of them fit in this low energy bonding state where the electron cloud is shared by both central atoms. We have no electrons left over for this antibonding state, which would drive them apart. And this is why, in isolation, hydrogen gas, H2, is stable. Now, we essentially solved that same problem, but for hundreds of atoms at a time with far more complicated elements than just hydrogen alone. But we're essentially solving the Schrodinger equation to get energies and forces, to update our trajectory, and we run this cycle subject to some set of initial conditions that samples what we want to sample. And in our case, what we want to look at is the sort of states that a system would go through under a plausible impact situation. So we've deconstructed this and idealized it into a computer simulation. So we have our simulation cell, which for context, this employs what's known as periodic boundary conditions. So you can think of it like Pong, where if an atom goes out one side, it comes back in the other side. This allows us to mimic what happens in bulk material buried within a comet. Now, we're interested in understanding how glycine and we throw some water in there for good measure, react when we submit it to or subject it to a cometary impact-like event. So we start from our ambient conditions glycine water mixture, and then when a shock wave passes through, two things happen. One, the temperature goes up quickly because we've essentially adiabatically compressed the sample to a smaller volume, and that leads both to a temperature rise and a dramatic increase in pressure. This sort of state is held for a finite amount of time, after which the comet would begin to disintegrate and blow off big pieces, small pieces, little fine grains, all sorts of cometary fragments. And those fragments will rapidly equilibrate in pressure with the surroundings. So you have a dramatic drop in pressure, which drives the expansion from this shock state to this expanded but still hot state. And then over a longer amount of time, that system will cool down back to ambient conditions as the particulates fall out and ultimately enter the biosphere. So we model that by having this four-stage system where we have our pre-impact, we drive a shock wave through it, we model the expansionary phase, and then we cool our system down. We essentially have an observation type experiment where we start with our precursor molecules, and we don't know what's going to happen. All we know is we're updating Schrodinger's equation and running and computing some trajectories for the actual atoms and how they move. And whatever follows is a consequence of that Schrodinger equation and the molecular motions themselves. So it's our task as molecular simulators to look at these simulations and interpret their results. When we do this with glycine, something rather surprising happens. Upon shock, when we've rapidly heated and compressed our sample, the glycine rapidly decomposes and forms cluster-like regions where they all start bonding together with a diamond-like bonding, with carbons tending to have, on average, 4 bonds. These clusters, though, once we go through the expansionary phase, rearrange chemically in a fairly dramatic manner. What starts out as globular clusters spontaneously and chemically rearrange into sheet-like molecules that have chemical bonding similar to graphite, the sort of honeycomb type lattice where a particular atom has 3 bonds on average rather than 4. Now, molecules that would contain just the pure carbon would be termed polyaromatic hydrocarbons, or PAHs. And in our case, because glycine has nitrogen and oxygen in there, these fall into a far more important category of molecules called Npaws, or nitrogen-containing PAHs. And why do we care about PAHs and Npaws? It's because these sorts of chemical motifs, in particular having the nitrogen embedded, makes these molecules important precursors for forming more complicated biomolecules and nucleobases. There's a bit more to the story, though. So it's been known for really decades that some of the earliest chondrites that have been studied on Earth have contained within them small Npaw molecules, such as uracil. We have our ring with nitrogens, and adenine. And these guys are important molecules to basically form those functional groups off of the backbones of a peptide, and we can start to build more important things like nucleobases from them. We also know that some of these molecules exist out in interstellar space, and possibly even within the peripheries of comets or other bodies like asteroids. But unfortunately, or fortunately for our study, these sorts of molecules really are not stable once they're brought within sort of the circumstellar envelope near the sun, where our rocky planets sit. In that sort of region, the UV radiation from the sun or for any star really, is sufficient to degrade and decompose these molecules spontaneously. So there's a survivability question of whether these molecules could even be delivered from interstellar space to Earth. Beyond that, there's also a question concerning synthesis and how these molecules might form out in interstellar space. And the traditional chemical routes to form them become energetically unfavorable once they grow beyond relatively small sizes. Isoquinoline is one possible endpoint for the spontaneous gas phase synthesis of these sorts of molecules. So what we find in our simulations by the spontaneous formation of these much larger Npaws is an entirely new and unaccounted for synthetic route that could form these molecules in situ during a cometary impact. Not only do they overcome the sort of survivability question that interstellar sourced Npaws would have, but they're substantially larger, more complicated, and have embedded on them and on their peripheries other functional groups that form spontaneously under these extreme cometary impact conditions. So all that needs to happen is for some secondary reaction to occur to splice these groups off, and then they can become part of a much larger chemical reaction network to form other things. Most of the molecules that we see form in these sort of planar sheet-like motifs, but we also find other complicated structures with multiple sheets that are joined together that form more 3D-like structures. By running these quantum-based molecular dynamics simulations, we have essentially to the atom level resolution to understand what is going on and why. In characterizing the chemistry during our model path, we find a few things of interest. So as I hinted at before, we see that during the initial shock passage, we form lots of diamond-like bonding in our decomposed glycine products. And upon expansion, these atoms bonding spontaneously rearranges from diamond-like structures to graphite-like ones. So this is consistent with our picture of what happened. At the same time, we can see why much of the chemistry that's unfolding as those Npaws form is the emission of terminal hydrogen atoms. So what remains primarily within the Npaws is our complicated heavy atoms of carbon, nitrogen, and oxygen. So most of the chemical changes occur during this expansionary phase as the cometary fragments fly off and equilibrate with ambient pressure. But during the cool down stage, another thing happens. Those molecules that are now in sort of sheet-like forms begin to unfold and expand and develop a very skewed aspect ratio where they basically form atomistically thin sheets with molecules being very planar in their shape. By using supercomputers, we can run many of these simulations at the same time to get a picture of a more statistical picture of the sorts of chemistry that occurs, because one simulation alone doesn't really give us confident bounds on the sorts of chemistry that might happen. But if we run many simulations, and in each one you see the formation of these large Npaw molecules, we can become convinced that this is the sort of chemistry that actually is dominant. We find various sizes of these Npaw molecules from our smallest here up to the largest, which basically consumed all of our initial glycine. Along with the formation of these Npaw molecules, we find other sorts of products that are still interesting. We form various chains. These are sort of like our peptide chains. We find other species that have highly reactive carbon-carbon triple bonds. And perhaps more interesting is we find species like ketene. Ketone's actually used in industry to form these sorts of complicated aromatic cyclic structures. And other molecules like guanidine are known components of other more complicated amino acids. Things like urea, carbomic acid, and acetic acid are metabolic products, which is sort of interesting in that we've essentially metabolized in a way, or accessing the same sorts of chemical routes that glycine would go through in a biological system. So the fact that we see these metabolic products gives us some confidence that our chemistry is reasonable in its predictions. So from this study, we found that impacts can really drive some novel reactions in cometary glycine that we know to be present there. The states reached in an impact can assemble this cometary glycine into highly complex Npaw molecules. These Npaws are important precursors to more complicated molecules like nucleobases and give an alternative route to formation of these molecules needed to form things like our DNA alphabet. Npaws formed during these cometary impacts are far larger and more chemically complex than those that are found through other means or formed through other means. And the shock synthesis route bypasses the known bottlenecks in the survivability of these sorts of molecules and gives an in situ way to basically form them right where you need them, right on your planet's surface. And that gives a route to forming these complicated molecules needed for the origins of life from very simple precursors. So that's roughly half the talk. In the next half, I want to share some more recent work that we'd actually just got published in Chemical Science as of this past Sunday, that looks at a far newer theory for the sorts of drivers for unusual chemistry. The idea here is that shearing forces near tectonic plates could promote the various sorts of chemistry of which we really don't know what will fall out of it. The notion that shearing forces can drive chemistry through mechanical means of actually straining molecules at the molecular level falls under a branch of chemistry that's known as mechanochemistry or mechanically driven chemistry. From experiments, a traditional approach that's become, over the past decade or so, the go-to route to accessing high pressures is what's known as a diamond anvil cell that literally is comprised of two small diamonds with a gasket between them that are squeezed together to form a micron-sized chamber that can reach many GPa in pressure. Certainly, hundreds of GPa are possible, but we're interested in somewhat more modest pressures. A riff on this experiment that's really new is the idea that you can rotate one of these diamonds with respect to the other to induce shear on the sample between them. This is what's known as a rotational diamond anvil cell, or RDAC. With this in mind, we developed a computer analog to it called a virtual RDAC to explore the shear chemistry in silico, because going to all the trouble of setting up these experiments is very expensive, it's time consuming, it's difficult to actually know what was formed unless you subject the resulting sample to a battery of tests. But with computer simulations, we can probe the same conditions and change out the sample and the various shearing conditions or the pressure to see if there's any possibility of chemistry occurring. So at the molecular level, we're modeling this in a relatively simple way. We have our diamond, we have a second diamond and a sample between them. We apply pressure in much the same way as the experiments do by moving one of the diamonds in a vertical way up and down. And then we apply shear by moving it from side to side at a constant velocity. So by applying a force down and a velocity to the side, we impose a physical friction force or shearing force on the sample. And much like our previous study, by setting up this sort of initial condition, we can sit back, let the Schrodinger equation predict what it will predict, and we can analyze the outcome. Now, a preface and a more thorough explanation of what we mean by mechanochemistry and connecting that back to regular chemistry, I think deserves some attention. So normally, chemists think of the world in terms of potential energy surfaces. You have these in astronomy too, where you consider the gravitational pull between two bodies, and that would have a potential energy well that would ultimately drive them together. Now, our energy surfaces that are predicted by the Schrodinger equation have bound states. For instance, wells that are associated with reactants, wells that are associated with various products, and it's the contours and the topology of the surface that dictate how the chemistry of a system evolves. In a particular example case, we can have our reactants and they have an energy well associated with them, and our products, which have an energy well associated with them. The energy difference, the height difference between these wells speaks to the thermodynamic driver for whether it's favorable to go from reactants to products. So that says something about spontaneity, whether it will occur or can occur, and what the ratio between the two cases, or the reactants and the products would be. But what dictates how fast that chemistry occurs is the barrier between how high this energy penalty is to go from our reactants well over the barrier to our products well, and potentially back again. Now, normal chemistry or chemistry in the lab that's not catalyzed is driven by the inherent temperature of the system, where at a particular temperature, atoms have on average a particular amount of energy. And if that energy is sufficient to go over the reactants, over the barrier from reactants to products, it will do so and go back and forth until there's an equilibrium between these two cases. But when we impose shearing forces or strains on the system, we can fundamentally alter that landscape, potentially in our favor. So if we reference everything to our reactants case, by applying a shear, we can change not only the barrier height, but also the overall favorability and change in energy to go to our product state. So in this sort of example case, we've, by applying a mechanical strain, have lowered the barrier for reactants to go to products, and also made the products far more energetically favorable than the reactants. So we need lower temperatures to go over the barrier, and once we form the products, they want to stay there. All of this results from underlying changes in the electronic structure that result from this molecular level bonding or bending and straining, where much as I had shown in our simple hydrogen case, we have our molecular orbital states that have electrons here, in this case in a bonding orbital and a non-bonding orbital, where this state here is what's called in chemistry the homostate, or the highest occupied molecular orbital. It's the highest energy state that electrons are in. And above that is what's known as a lumostate, the lowest unoccupied molecular orbital. If the energy difference between these two is large, you'll never get electrons that go from the homo to the lumo. But under strain, you can change those overall energy levels, and if they're made small enough, the thermal energy is enough to allow some occupation of this lumostate, which can drive the chemistry. So now for a movie. Hopefully this renders well for you. It looks maybe a little slow, but this is one of our simulations in action. So I've scrubbed all of our hydrogen atoms, which are our white colored atoms, because they're kind of chemically not the most important thing that we're really looking at. So we start from our glycine. And if you try and pay attention to a particular molecule, you'll notice over time that something surprising happens. By applying this compressive shearing force to it, these molecules begin linking up together and forming larger oligomers. This is all at room temperature. We haven't driven this to some high thousands of Kelvin state. We haven't subjected it to 50 GPa or 500,000 atmospheres like we did in the previous case. This is far more modest pressures, but we're getting the same sort of polymer or peptide backbone building chemistry out of this glycine system when we impose these shearing conditions. Now, normally, that chemistry that I had shown before goes through what's called that condensation reaction, where our two glycines join together, they form a peptide bond, and they eliminate water. But under shear, we do form some of this diglycine, this standard product. We form many other more complicated products that don't necessarily go through that condensation route, but rather amount to essentially forcing these glycine molecules to directly bond to each other. So in this case, this guy here is a glycine, and this guy here is a glycine, and we've directly driven a bond between them. We find a number of these different sorts of molecules that form under these conditions, producing not only linear chains, but some branched structures as well. This is highly unusual chemistry and a completely different path than the one that biochemists typically think of when they think of how polypeptides form. Now, from a materials point of view, what we see is as we apply bigger and bigger pressures or greater pressures, something interesting happens to the chemistry. At relatively low pressures, we start from our chemistry. This is what's known as a mass spectrum, where we essentially measure how many molecules are produced at a given mass, where mass is measured here in atomic units, the same that you would find on a periodic table. So we have a peak that signifies that we have glycine in our system, but also under shear, we find the formation of a molecule that's roughly twice as massive as glycine. So we formed some dimers or diglycine-like molecules. But as we increase the pressure, we form larger and larger molecules, as well as some with intermediate weights, until we get to our biggest pressures, where we form a wide spectrum of different masses of these molecules, starting from our initial small glycine molecules. Viewed in terms of their actual atoms and connectivity, we have our smaller glycine-like molecules. At intermediate pressures, these form molecules that have roughly twice the weight of glycine. And then under the highest pressures we considered, these form very complicated, long, extended peptide-like configurations. These are starting to look reminiscent of the bonding that one would see in a peptide or a protein. And all of this fell out of a completely different sort of chemical route than is normally considered in ambient conditions chemistry if you go to a university lab. But these sorts of conditions are totally accessible and relevant on a astronomical sort of time, pressure, conditions scale. The last thing that I want to leave you with in terms of a new technical idea is perhaps a little complicated, but I think we're on to something neat. Life and life-related molecules have sort of a strange quirk to them. Now, many molecules have what's known as chirality. That is, they have a handedness to them, where the overall groups in a molecule can be identical, but how they're specifically arranged about a particular center can have different symmetries. So in this case, we have a model of a simple amino acid that can have either a left-handed version, or if we reflected about a mirror, a right-handed version. And one of the big questions in origins of life research is why almost exclusively the molecules that matter to life fall in this left-handed category. This extends even to practical cases like pharmaceuticals, where, for instance, for a given drug molecule, the left-handed version can be therapeutic, and at best, the right-handed version might be therapeutically inactive, it doesn't do anything, or worse, it can even be toxic and cause some sort of harm. So understanding different chemical methods and synthetic routes that can form left-handed versions over right-handed versions or vice versa are of particular interest. Now, normally one would consider in a standard reaction, you'd form equal amounts of the left and the right. So something had to have happened in the past that preferentially formed left-handed versions of molecules from which we formed, or nature spontaneously formed, the first RNA and DNA-like molecules that then became self-replicating. Now, how this connects to our glycine simulations is interesting. Glycine itself is an achiral molecule. It doesn't possess a handedness to it at all. And its standard products are also achiral. So glycine by itself in its standard reactions won't form chirality. But in our shearing simulations, many of the products that form have these sorts of chiral centers. Here, let me see if I can pick out a couple. Here is one. Basically, what I'm looking for is a center that has 4 bonds where everything coming off of that center is different. In this case, this is one area. All of these have at least one, if not more. So what we've found is that by shearing, the shear-induced chemistry can make these chiral molecules out of achiral starting material. And what's unknown is whether, for instance, if we started from a glycine crystal that had some preferential initial order to it, whether we would form a left-handed version more frequently than a right-handed one. So this sort of shear chemistry opens up a whole new realm to understand why, or a whole new potential driver that could have formed stereoselective chiral molecules of the sorts that might have influenced why life is left-handed. So in this aspect, we've really only dug into the very surface level of this kind of chemistry. Mechanochemistry as a field is really only a couple of, it's really only as recent as the late 90s. But it's becoming a rapid area where scientists from all stripes, whether they're material scientists, they're chemists, they're physicists, are finding that by inducing shearing forces, you can drive all sorts of unusual things. And this is one of the big potential routes for forming new practically useful materials in the coming decades. But when we applied that sort of thought, those sort of thoughts to prebiotic chemistry, we found something rather strange, and that's that glycine will spontaneously form oligomeric chains when it's sheared. This gives a completely new abiotic route to form these sorts of polypeptide molecules, and could have even resulted in the formation of some of the earliest chirality in these biorelevant molecules. So with that, I want to leave a few concluding thoughts, and then I'll take some questions. One of these is that extreme conditions are really one of the new frontiers in understanding materials, material synthesis, and potential routes that have implications for things like the origins of life. We know that glycine is formed on comets, and that gives weight to some earlier theories about how we could have gotten glycine from space to Earth. But what wasn't really considered was what chemistry can happen during that impact process. By using computer simulations that can accurately model the chemistry, we can, in the computer, probe the actual chemical reactions that take place. And when we apply this methodology to understand how that glycine reacts, we find many things. We find the formation generally of complex molecules such as our Npaws molecules in the case of cometary impacts, or peptide-like chains in the case of shearing conditions. And all of these point to the behavior of materials under extreme conditions being both difficult to anticipate, but surprisingly rich and full of unexpected results. And as a scientist, it's really a gold mine where what's only limiting one is really sort of one's imagination for the sorts of cases that might have taken place. The actual underlying rules of physics and chemistry that drive how systems evolve really leads to some surprisingly rich and unexpected things. So with that, I'd like to thank you all for your attention, and I'm more than happy to take questions.
Thank you.
Let's see.
So I should see if there's anything in the chat. Unfortunately, Sarah had to drop out, it looks like.
If anybody have any questions, you can unmute yourself.
Oh, yeah, later.
So hopefully that wasn't too much of a chemistry overload. Or at least gives
Very
a window into an adjacent world in science.
Nobody's got anything. On the
questions?
computer, how do you write the algorithms to make it work?
So the question is, how do you write the algorithms to make it work? Now, want to just have in sort of the background this schematic. So there's a lot of moving pieces, as one can imagine. Now, a big part of this, so this really falls under what's called computational science as opposed to computer science, where we're concerned with how do we solve the equations that nature has given us to understand how systems evolve. So much of the separate pieces of this have been solved over the past, really few decades. Molecular dynamics, which is the notion of computing forces on atoms to update and propagate a trajectory, as a tool is really only as old as about the 1960s. Some of the first supercomputers at Lawrence Livermore National Lab actually were instrumental in performing these sorts of simulations. So there's the numerics of how you integrate this equation, which is we basically have standard numerical integrators to update our forces and positions in much the same way as if we had replaced this energy function with a gravitational potential and all of these atoms with planets or other particles. The exact same machinery would be directly applicable, and actually it is. That is one route that that computational astronomers can use to probe how things like galaxies will form their sort of elliptical shapes and evolve when they collide. So if you've seen those sort of animations of the Andromeda Galaxy and Milky Way colliding, this sort of particle-based simulation is at the core of that. So that's one aspect. And then the other is how we solve the electronic structure, which at the end of the day, without going into too much gory detail, we basically compute, how, through a bunch of integrals, how the overlap between the various atomic orbitals contributes to a particular interaction, and these form a matrix of entries which we diagonalize, and those And those entries are, the separate entries in the diagonal matrix are energies for the various energy states of the system. So this falls again back on basic linear algebra really to solve, and exploits math libraries that the US government had invested in substantially during the early days of computers back in the 1970s and 80s to perform this sort of linear algebra. And then people that are smarter than myself in terms of basic theory pull all of these things together into larger software suites that allow folks like me to think about the chemistry and the consequences when I set up one of these simulations, rather than the sort of nuts and bolts of writing, you know, thousands and thousands of lines of code. At the end of the day, most of what I do is writing hundreds of lines of code to analyze the outcomes of these simulations.
Thank you.
So I thought I heard some voices, but I didn't hear anything clearly.
We're taking it in. We're taking it in.
Yeah, sorry, I'm sure it's a little different than what you're used to.
Yeah, it is, but the slides were extremely helpful.
If I understand correctly, the data that you've presented basically says that there is a potentiality of organic molecules forming, not necessarily that these organic molecules are coming from the comet.
So what's coming from the comet, or what's on the comet that we know is glycine. And what we are simulating is how that glycine will ultimately react when it goes through the process of impacting on a planet. So we know the glycine's there. We know how the basic chemistry, you know, how basic chemical interactions is captured by the Schrodinger equation play out. So what remains is to actually do the numerical experiment to see what happens. Because of course, this is the sort of thing that would be a little difficult, although not impossible, to make a model of for an actual physical laboratory experiment.
Okay.
So you're assuming the water's on the comet that produces all the extra molecules, or do you assume the water's already on the Earth?
So the water is part of the comet. Comets are icy bodies, so there's water, there's glycine. There's actually a number of other species there as well, such as ammonia, and various other small molecules that we didn't explicitly consider in this study. But we know from the actual space probes that glycine was there and that water is there. And truth be told, the water actually is more of a spectator in these reactions. It's sort of there before and it's there after. And what really is reacting is the glycine.
Okay, thank you.
We have a question in chat.
In chat?
Yeah.
So the question is, why does one look for glycine as opposed to any of the other three molecules that form DNA? So actually, glycine itself is not part of DNA. It's not one of the A's, C's, T's, or G's that are the other amino acids that form the DNA alphabet. But glycine is focused on because, well, for a few reasons. One, we know it's out there. So that sort of supports the basic premise. But more importantly, glycine is the simplest amino acid, which means that we can use it and other people use it as a simple model for understanding how those initial bonds form that link, say, 2 glycines together or 3 glycines together, because that sort of reaction is more general to the other amino acids. But the difference for those other amino acids is that they have sort of different dangling functional groups off of them, where glycine is really just the simple backbone. So I have another question, and it's one that I don't really know how to answer because at heart, I'm not really a biochemist. The question is, I touched briefly on the question of chirality, and I think that the person writes, I assume that your systems are producing racemic mixtures, that is, equal quantities of the left and the right-handed form, and they're not enantio-enriched or enantio-selective. And what I can say to that first part is we haven't run enough of these simulations to really determine, and based on the starting material, which was just essentially a glycine in a disordered state, I wouldn't expect that by itself to bias towards forming the left or the right-handed form. But what could is if that glycine were in, for instance, a crystalline state where all the molecules assume a particular order. If you shear that, there's an initial order that might get imparted into later products. And in regards to favorite theories for why chirality formed, I really can't address that because it's something very new to me. So I don't have a full grasp of all of the theories that are out there. From a basic chemistry point of view, I look at the products and I see that they're chiral, and that points me down a path of saying perhaps these conditions matter. And really, that's where sort of the grant writing aspect of practicing science comes in, where you have, this promising idea and some notion of a new area that you want to get into. So you go and fight for money and hopefully get that money to do the work. So the next question is a physics one. Does the Schrodinger equation have anything to do with the Schrodinger cat? And yeah. It's the same Schrodinger. And the Schrodinger cat is really, this is going back to my physics days, is a macroscopic imagining of the notion that a system isn't in a definite state until you observe it. So what quantum mechanics says is that what really exists at a micro or a nanoscopic scale is a wave function. That was, in our chemistry studies, I don't know if my slide is showing, but in any case, in our computer simulations, we consider a wave function that represents the electron clouds for these various atoms that are interacting. And the Schrodinger cat is basically saying at a nanoscopic level, we don't know where an electron sits until we observe it. It could be in one part of an orbital or another. Essentially, that it represents the electron clouds represent this probabilistic nature of where the electrons might be. And in the Schrodinger cat thought experiment, Schrodinger ties a cat in a box to some quantum process that is inherently tied to this sort of inherent indeterminacy of the system. Until you look at it, you don't know what happens. So yes, in a sense, it is the same notion, although I haven't thought about the Schrodinger cat in a long time. My undergraduate physics book did have it on the cover, though. If anyone ever sees the standard quantum mechanics book for an undergraduate senior is a blue book by Preface, and it has a cat on the cover, and on the back cover it has a dead cat. Okay, so another question. Is it possible for plate tectonics to produce glycine? That, so I don't touch on this. This is actually some of the work from my PhD or my postdoc advisor, Near, that he first considered not in the plate tectonics theory, but rather the cometary impact theory, far more simple starting molecules like ammonia, so that's NH3, and some other simple carbon-containing molecules. And what he found when he performed similar sorts of simulations of the cometary impact process is that those very simple molecules can form amino acid-like molecules like glycine. So it's possible for even smaller starting material to assemble into something like glycine and then go on from there. We haven't looked at simpler molecules in the shearing sorts of simulations, but I wouldn't rule out the possibility that unusual chemistry would result. But at this point, we certainly know that glycine is out there on comets, and because of that, it's a plausible starting material. So you don't need to go back to, if anyone's familiar with the Miller experiments where they put, this was back in the 50s, I believe, where they put a simple gaseous mixture of things like ammonia and perhaps cyanide. I forget all of the hydrogen cyanide. I forget all of the constituents, but they put these simple molecules that they thought would be on the early Earth together in a flask, and then they zapped it with electricity. And what they found come out of that was a bunch of organic molecules, like various amino acids. That sort of theory has, or rather the specific composition of gases that the early Miller experiments considered isn't really the composition that scientists now think was present in early Earth's atmosphere. But there's certainly a body of work that would point to simpler molecules forming our amino acids like glycine, because glycine had to come from somewhere. It doesn't just spontaneously appear on a comet. The question just becomes, how far back do you trace? And if you can start with glycine, you've already done quite a bit of the work. So I guess one other thing, if I don't have questions that come in that I do, I think is worth highlighting is how, just to give a perspective, is how in sort of the modern day, many scientists need to operate in sort of an interdisciplinary or cross-disciplinary way, where some fields such as origins of life research are inherently pulling from biology, from chemistry, from basic physics and astronomy and all of these separate areas. And really, we're kind of in a new phase of science as it's being practiced, where the notions of a particular department or a particular discipline really break down. And what one finds is to sort of succeed in science is to find the niches between these different areas. And that can lead to some, very exciting new areas, such as this particular intersection of astrochemistry, chemistry, and astronomy. So the last question that I have here is, have I worked with the results of the Rosetta Philae mission? And no, I have not. That in practice, what someone like me does is we read the literature, the articles that those sorts of scientists produce, For instance, the papers where they showed the sorts of molecules that were in the chemical makeup of the cometary gas and coma sort of materials, and use that to inform the sorts of systems that we think are plausible. That as a computational chemist, I'm sort of a couple levels removed from, working directly with the data, except as far as it says there are these sorts of molecules present perhaps in these ratios.
Is there any research on how glycine ended up on comets?
So that, honestly, I don't know.
Because I can imagine
And why it would have formed there in the first place.
Yeah, I'm thinking that some material out of the oil cloud.
Like the early bombardment period, when you had, the sort of, what would one call it, the sort of nebular disk where the planets were forming and asteroids were getting flung out and cometary fragments were getting flung out, would have had many of these, extreme impact events between these various components. And, if something simple is there, the exact same simulations that I had described to you before that my advisor had run, starting from the simple molecules under shock conditions can form glycine-like molecules, that gives one potential route for why they would form and be present, after the fact on some celestial body like a comet. That, there's a very, very long history to those bodies. And it's often, from a human perspective, a very violent history in terms of the, impacts and temperatures and irradiation from, stellar bodies that it would have gone through. So there's many possible drivers, of which shock impact is one of them, and one that we do know works. So to elaborate on that question regarding the Rosetta Philae mission, so yes, I'm essentially taking the high-level data in terms of the sorts of molecules that are formed, and using those to seed these simulations to extrapolate what might form out of them. And really that is where my practice is in understanding, at a fairly fundamental level, the chemistry and mechanics of how these materials behave under extreme conditions. That much of the, by training, I really am more of an explosive scientist, but the same, sorts of explosive molecules are, carbon, nitrogen, hydrogen, oxygen containing molecules. They obey the same laws of organic chemistry. So there's surprising overlap, both in terms of the chemistry and the chemical reactions that take place, as well as the methodology used to study them. So what biases, someone like me, for instance, to look at the extreme conditions is coming from this world where what one tends to think about is detonation phenomena, situations where things are very, very hot and very, very high pressure, that, a different scientist who's, trained in a different area might look at the problem from a completely different perspective, and both can yield some very rich insights into the possibilities for how these systems will behave. And I would say that from the standpoint of biology, these sorts of impact ideas are probably, they're a fairly new idea, although they do go back at least to folks like Carl Sagan that were considering, this violent early evolutionary period of our solar system and what might have taken place during that time. Hopefully we don't form any of these molecules in this way on Earth in the near future.
Right.
But when you have on a cosmological scale, thousands of comets raining down over millions, if not billions of years to allow for chemical and eventual biological evolution to take place, the possibilities are really staggering. And I guess it can also show how you can start in physics and wind up in chemistry. Because at the end of the day, it mostly is solving a bunch of physics problems. Okay. This next question is, do these calculations require supercomputers, or can they be performed with off-the-shelf processors? So there's a few aspects to this. One is that supercomputers, modern supercomputers, are made actually with commodity components. It's just that we have thousands and thousands and thousands of them in many, in huge racks that folks at Amazon would call servers, but we call them supercomputers. Gone are the day where you have these, highly dedicated Cray architectures or other computing architectures. So what separates work is really how many of those processors you need to execute it. Now, a single simulation of which, the results that I showed, were formed from many, many independent simulations. One of those simulations I could run on my desktop, and it would take, order of a few weeks to run to completion. And in practice, I run, hundreds of these jobs, if not thousands, for a particular condition to do some statistical sampling. Each of those running on a separate core of a supercomputer over those same 2-3 weeks, if not more. What I don't highlight in this talk is sort of a different class of problem where we're really looking at systems with millions, if not billions of particles, and those inherently can really only be performed on the largest supercomputers. So in many cases, a single simulation or a small version of a simulation can be performed on, someone's desktop computer. In fact, I do that to some degree especially, if I'm testing something out, because it's quick and easy. But anything production requires, the concerted power and processing power of thousands of, if not millions of or at least tens of thousands of processors. Okay, so I'm still processing this question, but the notion is that this sort of research where we're looking at prebiotic chemistry, that's pre-biology chemistry, is perhaps more plausible in terms of explaining how life would have formed, rather than the theories that some microbe was on a comet and went through the impact process and landed on Earth and seeded life. Well, I can't necessarily speak to the probability of that. The survivability aspect of even simple organisms surviving that type of impact event, well, not negligible, because you can have various, you can have the comet, for instance, hit dead on or just graze the surface of a planet. And all of those will produce sort of different temperatures and pressures, some of which may not be completely hostile to a simple organism. But I would say that this sort of research really fits into the the camp of, we think that life formed on Earth. Perhaps some of the early chemistry happened off Earth, but most of the important steps happened here. Or another aspect, and one that's not always highlighted, is when it comes to origins of life research, we focus on the Earth, but perhaps the bigger question is whether or not the same sorts of things are happening elsewhere. If you have, billions of planets to sample from, and it only needs to happen on, if it only happens on a fraction of those, and the next steps only happen on a fraction of those, that's still a lot of planets. Or potentially even moons in our system. This, particularly the tectonic shearing idea, is really more focused on the sorts of conditions that are relevant to like Enceladus and other moons of Jupiter and Saturn, or Europa, that have that are known to have these sorts of icy crusts with potentially some liquid water underneath, and that we know from other astronomical observations are tectonically active because of the tidal shearing forces induced by orbiting such a large massive star, or not star, such a large planet, that some of those moons themselves are tectonically active. But as from the point of view of the computational chemist, what we're interested in understanding is the plausibility. And it's down to, folks like astronomers or physicists to say, this particular body has, these sorts of conditions to which, particular aspects of the chemistry may or may not apply. So in many respects, this sort of computational work tends to go, years, if not decades ahead of where the experimental science, in terms of like physical lab experience or sending probes places kind of science lies, that it gives a notion of what is possible and what might be of interest to look for. For instance, the sorts of spectroscopic signatures that one would look for those Npaw molecules can be used to say, well, we want probes to have, what one would call like a vibrational spectrometer, or an IR or an infrared spectrometer that's sensitive to molecule vibrations in a particular range, because we know the characteristics of those molecules. So we might have some idea of what to look for. And actually, for a large subset of astrochemistry, it's looking at, one really looks at light from bodies which has encoded in it distinct spectral lines that correspond to specific vibrational motions or electronic transitions. And that's how someone can have, sit on Earth and look at the light emanating in much the same way the light emanating from a star, what elements are in there because of this spectra. The same sorts of concepts apply to finding these other molecules, but you need to know where to look. And you need to know what your probe should be sensitive to in the first place. Is there a possibility ultimately for laboratory experiments confirming the impact pressure and heat simulations? So I actually didn't get into this in detail, but the short answer is yes. And to some degree, the experimental analog of these simulations has been done. Now, I forget the exact dates, but within the past 10 to 20 years, there's a Japanese group that looked at performing shock experiments on icy glycine mixtures. They basically cooled samples down, and there's a few different routes, one of which you literally impact a massive a massive flyer plate at a sample, and this generates a shock in a target. And more recently, doing a tabletop version where you shine lasers on like a thin plate of aluminum, and this will launch a little plasma of aluminum that then impacts the material and generates a shock in it. So there's experimental routes that are complementary, but what I didn't get into, and is worth mentioning, is that these sorts of experiments were performed on simple glycine mixtures, and what they found was actually surprisingly similar in that they specifically knew to look for things like the glycine oligomers, whether you formed diglycine or triglycine. But what they also noted was that when they did a census, a mass census of where all their glycine went, what was interesting is that they couldn't account for it all. So they found glycine, and then after the experiment, they found some amount of glycine, diglycine, and various oligomers. And then there was this missing bit, but they noticed that there was residue left over in their experiment that looks like soot. The same sorts of molecules that are, that build up in your engine. And as someone familiar with detonation chemistry, we know what soots look like, and surprisingly, they look a lot like those Npaws molecules. These, extended aromatic structures. So while they couldn't identify what those molecules were and what that soot and residue was, I think there's a good chance that if one were to perform the experiment again, knowing what to look for in the analysis, that they might find, the glycine soots that formed were in fact these biologically relevant Npaws molecules. And I guess the other aspect that sort of highlights, and why ideally one does this sort of science in a group setting where you have both the modelers and the experimentalists together, is that as a modeler, we can run the simulations and we can actually look at what the computer says. You're forming molecules that look like this. What the experimentalists see is, well, a wave moved through and it moved a little slower here or a little faster there. We recovered our products and we ran them through some sort of mass spectrometer and found ones that look of this size or that size. There's a far more ambiguity in the experiments that the computer simulations give a lot of direction for the sorts of analyses you might apply to a given experiment or the results of that experiment to better understand what actually happened or took place. And that's why institutions like Livermore Lab, really emphasize the sort of interdisciplinary approach to work, where you have a bunch of different scientists of different backgrounds that are all focused on the same set of problems, so that they look at things, with their own perspectives and are sharing ideas about how one might look at and analyze these results. So in some senses, this is a little microcosm of, what one would have in practice of being more of a big science type problem. Because no one person on their own can really, figure it all out or determine it. All we can do is sort of talk with each other either through the literature or directly in order to devise better experiments and better models and better connections between the two to understand how the world works.
Any more questions?
Well, I'm very thankful that you all invited me to speak. Hopefully this wasn't, so far out of field that, nothing was gained. I'm not the person to tell you how to put together a telescope or how the galaxies evolved, but it is amazing how the same sorts of computational approaches, in particular these particle-based simulations or dynamic simulations, really can be applied to both the very big and the very small. So there's far more overlap in both how one addresses the problems and then how one actually performs the experiments or the simulations, and then the sorts of bodies of work that one needs to pull from then really meets the eye.
Well, I saw your presentation given at another location and knew that we would be delighted to hear you give this talk. Thank you so very much.
Well from other chemists.
Oh, we appreciate it a lot. Thank you. Yeah, your slides were also really, really helpful. I'm glad it's recorded. Thank you.
Yep.
Yep.
Thank you.
To those joining us, the talk will be available on both our Facebook group and on YouTube for as long as they are archived there. So they're both a resource and for anybody who missed a part of the talk, you can go back and revisit.
Or wants to review the slides.
Yeah.
Thank you. Thank you very, very much.
Thank you.
Bye, Liz.
Bye, everybody. Thank you.
Bye. Bye-bye. Thank you all.
Have a good night. Stay safe.
Yes, indeed.
Hope to see you